So when you consider where we've been and where we're going, I am confident that we have exactly what it takes, and we have the ability to leap from the caretaker mode back into the dare-taker mode. And if you take a look at the mission directorate AAs that are in place now, we are very, very fortunate to have very strong and solid thought leaders in key positions within this agency. I'm very thankful for that. And so with those kind of people in place, we leading our organizations to accomplish the agency's goals, we're in a very good place with the ability to be able to carry this out. So today, our mission directorate AAs and some of their delegates, two of their delegates, two people were not able to make it today, are here to share with you some of the accomplishments that they've done in their individual organizations, but more importantly, where are we going in the future? What do we have to get excited about for a future for this agency? And so I'm looking forward to hearing from them. I know all of you are, about what's in store for this agency. So the first person that's going to be coming up to talk to you guys is Dr. John Grunsfeld. And of course, he does not need an introduction, but I'm going to tell you just a couple things about him. He was named the Associate Administrator for the Science Mission Directorate in January of 2012. He previously served as the Deputy Director of the Space Telescope Science Institute in Baltimore, managing the science program for the Hubble Space Telescope and forthcoming James Webb Space Telescope. He's a veteran of 5 space shuttle flights and visited Hubble 3 times during these missions. He also performed 8 spacewalks to service and upgrade the observatory. And one thing you may not know is 20 years ago today, he was actually on orbit doing operational performances. So please welcome John Grunsfeld.
Well, as always, it's a pleasure to be here, and as Harley knows, I usually don't start thinking about what I'm going to talk about until late the night before. This year is no exception. Last year, how many of you remember my talk about billions? Anybody who's here? A few hands. Well, I can't get away from numbers. I'm a physicist, and so this year's going to have some numbers too. But one thing I'm going to assert right off the start is we're not in caretaker mode. We're also not in undertaker mode. And I hope to convince you that a little bit, but if you were watching just the slides playing in the background, which are the best of 2014 pictures, the Goddard missions, that page filled with tiny dots, it's clear that we're doing a lot of very ambitious, audacious things. Bob Rogers has given a number of really insightful talks to us, and I hope all of you listen to that talk very carefully. He has another shtick, if you will, talk that he gives, which is about story. That NASA has wonderful stories, but we don't tell wonderful stories. I think we're getting better. I think Lauren Worley left. She and I talk about this frequently, as I do with David Weaver and Dwayne Brown and others. We approach story making in almost the same way that we approach engineering. We say, okay, we're launching a great mission. Let's break it down into its component parts. We'll describe, the science. We'll describe the program management. We'll describe the schedule. We'll describe the budget, and we'll describe what we think the science that will come out of it. That's not how everybody else in the world thinks. You have to have heroes. You have to have villains. You heard a little bit about that. I'm using this cover slide. Why? Because I'm a Hubble hugger. You all know that. I carry Hubble over my heart, thanks to Land's End and others. But and these no iron shirts. I wouldn't live without that. But Hubble is an amazing story. Just an amazing story. We could not have created the Hubble story if we wanted to. It's too fantastic. So I'd like you to heed Charlie Bolden's ask of all of you, which is to go out and tell stories. Go out and tell your neighbors' stories, your kids' stories. You get to do, and we get to do, amazing things. But it's all for naught if we don't share that. So I wanted to start out with, sort of my end point. Maybe I'll get there a little bit later. Along those lines, I'd like to start out with what I think we do, what our mission is. And particularly our mission in science, but it applies to all of what we do at NASA. We innovate, we invent things. When we innovate, It allows us to go explore. When we explore, we discover things. And I'm convinced that woven into the genetic fabric of humans is a desire to discover things. If you really want to know, it's the gene DRD4 R7 variant, but that's a whole other story. I won't talk about that. And when we discover things, it gives us the ability to inspire the nation, the world, and the young people who unfortunately aren't in the room at the moment, but maybe they'll come back. This is my engineer's view of the story of innovate, explore, discover, and inspire. But it is our central thinking around, or at least mine, why we do Earth and space science. And it really starts with the beginning of the universe, the creation of the first elements out of this primordial soup of exotic particles, condensed out, protons and electrons. Protons and electrons combined, we get neutrons. Of course, a lot of other particles around, but eventually we got hydrogen, helium, and a tiny bit of lithium. Now, if that was the whole story of the universe, life would be pretty boring.
And we'd all talk really funny.
Because of the helium. But in fact, stars formed, chemical elements inside of those stars formed, and the beginning of the amazing story of life began with the creation of the chemical elements that we're made out of, the calcium in our bones, the iron in our blood, the oxygen that we breathe, the carbon that we're made out of, the water that we drink. All of that started inside of stars, processed through galaxies, processed through the evolution of the universe, the expansion of the universe, to the creation of planets. From Kepler, we now know that when stars, and Hubble and Spitzer and ground-based observatories, when stars form, planets form about the same time, and we are surrounded by planets. Basically, Kepler has shown us that every star in the night sky that you look at has a solar system around it, a significant fraction of which have rocky planets, and a significant fraction of those have something rocky like Earth. Now, we don't know that yet, but statistically, we infer that. I'll talk more about that later. The likelihood that there's another place like Earth nearby is pretty high. And we want to study that the physics, the chemistry, the molecular interactions, the creation of organic materials in molecular clouds that then seeds those planets that allows life to exist on Earth that probably does elsewhere, to be able to answer that big question, are we alone? Now that's a big fundamental question that we all really want to know the answer to, and we are on the cusp of being able to do that with a future telescope. But at the same time, we're able to study our own Earth in great detail, and we're able to look at the physics in detail, the chemistry of how our own planet works, and we can ask the question, is human life sustainable on planet Earth? That's an open question. Now, I can tell you the answer right now and make my talk very short. The answer is no. It's not. And actually, we know that with some certainty because in some 5 billion years, the sun will have run out of fuel, expanded, it will be inside of the envelope of the sun, and we'll be burned to a fiery crisp. Now, I'm not going to worry too much about 5 billion years from now because long before then, Andromeda is going to collide with the Milky Way, and we may just get ejected. So I'm not going to worry about that. Of course, that's still a few billion years away. More likely than not, within the next 50 to 100 million years, we'll get slammed by some potentially hazardous asteroid, which will turn out to be actually hazardous, and we're working on that too. But that's millions of years. So what do I worry about today? Well, not today, but tomorrow. I'm responsible for a lot of things, and tomorrow is 3/12/15, and at 22:14 Eastern Daylight Time, we're going to launch the MMS mission, and you heard about that. And even if you're not a heliophysicist, this is an incredibly exciting mission. It involves rendezvous of 4 satellites around the Earth, changing constellations, this is formation flying, and studying a physical phenomena that's pervasive throughout the universe, magnetic reconnection, something we understand very little about, and which is an energy transfer from the solar events, coronal mass ejections, disturbances in the magnetic field of the sun, how that gets transported into the Earth's atmosphere. Really amazing physics, and it's going to be a very cool mission to watch. March 14th, 2015. Any guesses? 3/14/15, 9:26 a.m. Use the opportunity on Saturday, after the successful MMS launch, to celebrate Pi Day. It's just a cool thing. Science is cool. Math is cool. Go out, all day long and tell people, hey, you know what day it is? July 18th, 2018. Don't hold me to this date. 7/18. Solar Probe Plus. We're making great progress. This is a daring mission. We're going to fly into the atmosphere of the sun and orbit the sun inside of the sun's atmosphere. Really an incredible mission. I've told this joke too many times, but to make sure the spacecraft doesn't burn up, we're going to go at night. Okay, January 13th, looking a little bit in past history, 131:15. Charlie mentioned this. Can you crank up the volume if it's not already up?
And we have the brake wires. And spacecraft separation. Good spacecraft separation. The SMAP payload, the soil moisture active passive spacecraft, has now successfully separated from the Delta II launch vehicle and is flying on its own.
Okay, so you heard two things that I think are really great, one of which is the soil moisture active passive is flying on its own, and the Delta II vehicle, and those were amazing photos, thanks to ULA. But we had a successful Delta II mission, which is just a wonderful rocket. Soil moisture active passive is on orbit. We don't have images of it now, but the 20-foot antenna has deployed. That's audacious. It hasn't started rotating yet, but we're getting close. But we have turned on both the passive radiometer and the active radar, and we started to take data, and it's all working. This is a critically important mission. It's going to look at soil moisture in the top few centimeters of the soil, which accounts for only a tiny fraction of a percent of all the world's fresh water. But it turns out to be critically important water for a variety of reasons, one of which is just the dynamics of the water cycle. But the other reason is, we are entering, what a number of scientists have called a phase of a nascent mega drought. It's very bad. California is already in, now this is the U.S. Drought Monitoring Center, calls it an exceptional drought. Every indication is that this is going to continue and that over the next 85 years, which is how far the most recent projection I saw, that it only gets worse. And I'll point out, California, Texas, Oklahoma. Now, in Oklahoma, at least what I heard in the Senate a couple of days ago, this will get me in trouble, this is not real. But we're measuring it. We're measuring it around the globe with soil moisture active passive and our Global Precipitation Mission Core Observatory and the whole constellation, understanding this water cycle from the viewpoint of space, doing calibration and validation on the ground is all absolutely critical activity to answer that question. Is our life sustainable? Is our way of life sustainable? These are very important questions. First, snapshots. So hopefully you've seen this, but if not, selfie, maybe we're trying to get a new term, snapshots. These are the ground traces from soil moisture active passive, showing that we're alive. Once it starts rotating, those swaths then get wide and we cover the whole globe. March 6th, 2015. Just amazing. We entered orbit around Ceres. This is the first mission that's orbited two different solar system bodies, Vesta, now Ceres. And we're going to start to get just unprecedented views. And even from the distance, we see that Ceres is a whole new world, and there's those two bright spots. Of course, those are the cities on the Death Star, but we have no idea what those are at the moment. It's an old crater, but it could be some fresh excavation of ice. New science. Everywhere we go, we discover new science. Just an incredible mission. Dawn at Ceres. July 14th, 2015. 750 EDT. Closest approach of the New Horizons spacecraft around Pluto, the second dwarf planet for us to visit. Ceres is the first. And don't blink. Be watching on the 14th because it's a quick flyby, but we'll get lots of images. This is our first view of Pluto. Really just an incredible, well, Hubble is the first view. Better than Hubble. I rarely say that, but it will have higher resolution than Hubble as it swings by Pluto. And because of Hubble observations, we have the opportunity potentially to go visit a second dwarf planet after New Horizons swings by Pluto. August 2017, we're going to launch a mission called the Transiting Exoplanet Survey Satellite. We know that Kepler has discovered all of these planets. They're far away. They're hundreds of light years away. What do we want to know? Who are our neighbors? Who are the closest planets to us? Where is the closest Earth analog? And subsequently, is anybody home? We won't know where the closest, whether anybody's home with Transiting Exoplanet Survey Satellite, but as planets orbit between their host star and the Earth, we'll see those little blinks of light, and we'll be able to catalog where all the closest transiting exoplanets are. And if they're transiting, it gives us the potential to be able to interrogate their atmosphere and see if there are any signs of life. And so we're going to get a catalog of thousands of exoplanets from the Transiting Exoplanet Survey Satellite, so that another spacecraft CO2 in the atmosphere, or perhaps water vapor. Not the telescope that's going to tell us necessarily is anybody home, but it's going to give us a big step in that direction. We'll be able to identify the characteristics, the temperatures, perhaps even if for the closest planets, maybe some indication of what the structure of it is. James Webb Space Telescope goes where no Hubble has gone before. And I'll point out that when James Webb Space Telescope was designed, we only knew about 9 planets in the universe. And the trend wasn't good. We went down to 8 planets. And then with the launch of Kepler, the number is now, and ground-based telescopes, we're over 3,000 planets. If we were to design a telescope specifically intended to make progress and discoveries about exoplanets, this is what we would design. But it's also going to give us a glimpse at the very first stars and galaxies, the origins of structure in the universe, the beginnings of how planets form. It will be able to see through the dust that Hubble can't see through. So I'm just going to conclude with a few of the slides that show the missions that we're doing. It's a very bright future. We're on the cusp of discoveries everywhere with the Solar Probe Plus, with MMS, with Solar Orbiter, our international collaboration with ESA, and our whole suite of missions at scale, but also with CubeSats, with rocket flights, with high-altitude balloons, and heliophysics, with our constellation of wonderful Earth science missions. You heard about our 5 missions that we launched last year. You can include Discover, which is on its way to Earth-Sun L1, a collaboration with NOAA, which also has Earth viewing instruments, and many missions coming up, both to the International Space Station, hosted payloads, and as free-flying satellites. We've just recently directed the Goddard Space Flight Center to start working on the PACE mission, and in addition, a sustained land imaging program. This is absolutely critical for the future of agriculture in the U.S., of drought monitoring, of pretty much everything we do. And we have a plan for a sustainable program to follow on the successful Landsat 8. In planetary science, we're doing incredible missions. You heard about Ceres, Pluto, New Horizons, but Juno is going to arrive at Jupiter. We're going to launch the OSIRIS-REx mission to go to a potentially hazardous asteroid, Bennu, and do a touch and go, grab some samples and bring it back to Earth. And of course, Charlie mentioned, and InSight is going to launch next year to Mars. It's a geophysical monitoring station. The first time since Viking, we've had a seismometer on the surface of Mars. And just to prove we are a learning organization, on the 2 Vikings, we put the seismometers on the landing pads, and we discovered that wind on Mars causes seismic vibrations in the landing pads. Okay, so we're not going to do that. We have a robotic arm that's going to set the seismometer down, put a cover over it so wind doesn't blow it around, and also a heat flow experiment. Very interesting mission. The first time we'll look inside of Mars rather than just scratching the surface. And then Mars 2020 is a rover that contains, and Greg may talk about it, maybe not, or Steve, we have a collaboration between the mission directorates to put an in-situ resource utilization experiment on board. It's actually the largest experiment. It's going to bring in atmospheric carbon dioxide, break it into parts so that we can then store oxygen. So it's the first time we've actually got a working ISRU on the surface, and great science instruments and some little sample containers where we're going to put the highest priority samples that, if we can get them back to Earth, would give us a lot of leverage with scientific instruments here on Earth, scientists analyzing those to see if we see signs of life. Already on Curiosity on Mars, already with Curiosity on Mars, I have a slide coming up, but we've seen evidence of organics captured in the rock that's 3.5 billion years old. Now that's a hard trick to do anywhere. On Earth, very hard to find, essentially, I call it molecular fossil evidence of previous life. We don't know whether the organics, it's a chlorobenzene, we don't know whether that's evidence of past life. We do know that Mars was habitable for hundreds of millions of years. It had freshwater lakes, it had streams, river deltas, flowing streams down mountains, probably snow-capped peaks, puffy clouds, blue sky, a whole cryocycle and water cycle for a long period of time. Saltwater seas, we also know that. Recent evidence that it had a northern ocean or northern sea. Really a remarkable thing. But it was 3.5 billion years ago, and something happened. Maven is going to tell us what happened, hopefully, and Curiosity measurements of isotopes. For the first time, we've been able to determine that there was a habitable environment and date it using the Mars rover's great isotope capability. So Curiosity is still going. Mars 2020 is going to extend that. And we're working on plans for the future beyond that. We're also starting with this budget request a mission to Europa. We've been working on it for a couple of years. Europa is an incredible opportunity to see if there's somewhere else that might have life today. Do we know that there's any indications? No. But we know just from 11 flybys of Galileo, some Hubble observations, that it has an icy crust, a big ocean, and a rocky core. And that ocean has been like that for billions of years, a salty ocean. And there may be geothermal activity, just tidal heating from Jupiter. Hubble recently made some tantalizing observations that there might be plumes of water shooting out from that ocean. Well, we have plans to fly a mission that will make multiple passes by Europa. We'll do wonderful science, and we're working on plans for how do we interrogate those plumes to see if there's signs of organics or even signs of life. I mentioned Curiosity is roving around, doing great work. It also saw a methane signal. For a couple of months we saw methane and then it went away. What's that? What's that all about? Well, methane is an organic molecule, but it's also a geophysically relevant molecule. So we're at the cusp of discovering great things about whether there was possibly life on Mars, whether there might be life on Mars today. And we're also working on getting life to Mars, more than the contamination we've sent, even with our best efforts. But we're working with human spaceflight technology, the rest of NASA, to try and get a plan together so we can send astrobiologists and planetary science to Mars, because then we'll make the greatest progress in trying to figure out, does Mars have life, and then also to push the case that we can support life on Mars. In astrophysics, we have our great observatories. I mentioned the Transiting Exoplanet Survey satellite. We're putting NICER on the International Space Station, which is not only a great mission to study neutron stars, but will also allow us to test out celestial GPS using neutron stars as the clocks. Just a fascinating mission, and many more. We have a roadmap that's somewhat notional, but many of the pieces are there to try and study exoplanets to answer that question, are we alone in the universe? And it really starts with ground-based and Hubble, Spitzer, Kepler is added, the puzzle piece that says planets are common. TESS will give us our closest neighbors. JWST will allow us to study those. And we hope that we can start work on a telescope that's WFIRST or AFTA, which will both study dark energy, dark matter, the evolution of the universe, but also have a coronagraph to study planetary atmospheres in more detail. And we're on the cusp of being able technologically to follow on the technology from James Webb Space Telescope and Hubble, and maybe even servicing to build a telescope that was outlined as for technology in the most recent decadal survey, but some large telescope that actually has enough light collection power to get a spectrum of a potential Earth-like planet that would be able to see biosignatures. And on the cusp, that means if we decided to start building it today, it could be operational in 15 or 20 years. We have the technology, we have the capability. April 24th, 2015, at 8:33 Eastern Daylight Time. You know where I'm going with this. That's when Charlie Bolden and crew launched on STS, the space shuttle, to launch this beast, the Hubble Space Telescope. I hope you will all join all of us in celebrating Hubble's anniversary and saying happy birthday. And we're going to have celebrations all throughout the year. And as always, you can read more about all of this at worldwideweb.nasa.gov. And I'll say this, but I know it doesn't apply to any of you. If you have way too much discretionary time, you can follow me on SciAstro. So, with that, are you going to introduce Greg? Or? Okay, thank you very much.
Okay, our next speaker is Greg Williams, and I have had the pleasure of knowing Greg Williams and working closely with him since 1999, when we both worked together in the Office of Earth Science under Ghassem Asrar. So I can see very clearly why Bill Gerstenmaier drafted him to come over to the, I got a chance to see firsthand his ability to do, road mapping and strategy and policy development and implementation. So I can very clearly see why he was drafted to come over to HEOMD. In 2012, Gerst brought him over to be the Associate Administrator for Policy and Plans in the HEO Mission Directorate. In this capacity, he assists the HEO Associate Administrator, Bill Gerstenmaier, in charting the future course of NASA's human exploration programs. He works to both shape and respond to the policy environment in which the human spaceflight programs are conducted, both internal and external to the agency. The one thing that you may not know about Greg is that he has been married for 17 years now, and his wife has never, ever seen him without his beard, nor have I. So please join me in welcoming Greg Williams.
Thank you. It's good to be here this morning. This is a great venue in which to bring the exploration and science and technology communities together to really talk about where we're headed. And I can only echo what John and Charlie both said. I hope you'll go out of here telling stories about the future that will engage the public and all of us in our next wave of exploration.
There you go.
Thank you. Okay. See if I can do this without hurting anybody.
Right, and just don't touch the bottom.
Just don't. Okay. All right. Thanks. I wanted to start with this image for a number of reasons. One is it really speaks to what we heard earlier this morning about going back to dare taking. The idea of a journey to Mars is an enormous dare taking undertaking. It's a long time away, but we're, as I'll hopefully convince you shortly, that we're about to get started. The other reason why I like this picture is that it starts off talking about science and exploration and technology integration, which is an important theme for us at NASA, working across our mission directorates. Science Mission Directorate, where was my former home, is of course a science-driven culture, and the Exploration Directorate, where I'm at now, is an engineering-driven culture. The difference, I think, was articulated already this morning. John can tell you, from the science perspective, what genes are responsible for our exploration desires. In an engineering culture, we know that genes generally come in blue. The other reason why this is important is the planetary defense aspect of what we do. You can see that Mars, having lost most of its atmosphere, is now sucking away the Earth's. And the other reason why I like to show this image is that it conveys, if you could read it across the bottom, the paradigm, the framework in which we in HEO are thinking about future exploration, progressing from an Earth-reliant phase where we are operating in low Earth orbit, principally on the International Space Station, where return times are measured in hours, wanting to get ultimately to an Earth-independent frame of exploration where return times are measured in months or even a year or two. And in order to be able to do that, we need to pass through, as Charlie mentioned earlier, this proving ground of being able to operate in cislunar space with return times in days, and really test out the systems, the technologies, the operational techniques that are going to be required for long-duration spaceflight. As Charlie mentioned earlier, it always seemed that we're 20 years away from getting to Mars, and that's still true. What's different about today is that we actually have in development many of the major pieces that are going to be required for human exploration of the red planet, and you'll see some of those details coming up here. It starts, of course, with the International Space Station. This is a photograph taken from STS-135, the last shuttle to leave the ISS, and it's a poignant reminder of what we've accomplished, what was accomplished by the shuttle program in addition to deploying the Hubble Space Telescope. Its second job was building the International Space Station, and it accomplished that very well. This last week, another amazing accomplishment, Barry Wilmore and Terry Virts conducted 3 EVAs within the space of 8 days from the International Space Station. And what they're doing in those set of EVAs is they're rewiring some docking ports externally to prepare for the installation later this year of an international docking adapter. That international docking adapter is going to allow vehicles of any kind, of any origin, that designed to that spec to be able to dock with the space station, including our new commercial partners, Boeing and SpaceX, when their systems are ready by the end of 2017. Also, this month, in fact, starts the 1-year increment where Scott Kelly and Mikhail Kornienko will begin a tour of a 1-year research program on the International Space Station. Russians have, of course, flown for over a year before. What's different now is that we have a whole new set of medical protocols, a whole new understanding of what needs to be measured, how to measure it, and how to use those measurements in order to advance our long-duration spaceflight capabilities. And then uniquely, we have the advantage of Scott Kelly's twin, Mark Kelly, who will be here on the Earth, and we'll be able to compare their genetic situation, their responses to stimuli, in order to understand and measure precisely the difference in an ideal state, an ideal sample, a control case on the ground with the subject on orbit. So very exciting, and this is going to start towards the end of this month. Before leaving out into space, I just wanted to say that ISS also enables us to look down. It also allows us to think differently about, or maybe more broadly, about what robotics really means. We like to think, because of the movies, I think, of human-looking robots and with arms and legs and so on. But robotics, really, from a utility standpoint, is more like this. This is the automated installation of RapidScat on the International Space Station. A truly astounding engineering endeavor. And RapidScat, shortly after this installation, was turned on and began rotating and is now operating and producing great data on the research community and also for our partners in NOAA.
So next command is K17 set.
This is one of these great tense moments. The thing's been installed. We're going to start sending commands to it. Is it actually going to work?
Next command is K18 set.
And it works. Again, this is an example of what can be accomplished with humans and robots working together to produce scientific data and engineering exploits that would be impossible otherwise. Okay, then moving outward, and this is where now the next wave of dare taking really begins with the exploration systems programs. We've been operating with humans in low Earth orbit now, again, ever since Apollo. We're now beginning to prepare for human operations beyond low Earth orbit through the Space Launch System, the Orion Crew Capsule, and the ground systems that support those. Again, this is just to show you, I don't need to tell you in this crowd, but I need you people in this crowd, as Charlie said, to tell other people that Orion and SLS are not PowerPoint programs, they're not paper programs. There is hardware being developed, being tested. You all saw the EFT-1 launch, entry and recovery this last December. We're all actually now preparing to begin the version of EM1, sorry, the version of Orion that will fly on EM1. The lower 2 pictures on the right are barrel system component manufacturing that's already taking place at the machine assembly facility. Similarly with SLS, Real hardware is being developed. Charlie mentioned the RS-25 engine firing at Stennis. He also mentioned that today is the QM1 motor firing for the solid rocket motor. That's where Bill Gerstenmaier, my boss, is today. He's an engineer, so it's like, okay, rocket motor firing, Goddard Symposium. Rocket motor firing, Goddard Symposium. So he's there, and I'm here, and we're both glad to be doing what we're doing today because both these things are important. But SLS is off and running. Again, tooling's been established and installed at Michoud. Barrel segments are already being manufactured. And then the ground systems, Charlie mentioned the recovery ship, the Anchorage. It's a photograph of it swallowing up Orion. And then the mobile launcher is being modified at the Kennedy Space Center, along with the VAB and everything else we need to launch these spacecraft. And then when they're ready, they're going to be, again, launching on several missions into the proving ground of cislunar space. This is just a short list of what we need to accomplish in cislunar space while we have those capabilities. We hope to get to a flight rate of once a year after we have the first crewed mission of SLS and Orion. And we need to demonstrate how we want to operate in deep space. We need to be able to test key operational systems. We need to be able to develop techniques like in-situ resource utilization. We need to establish operations with a reduced logistical capability. This is an important thing to understand. A lot of people think of logistics as kind of boring, but in fact, logistics is the key to the future. Exploration of deep space is as much a logistics and a supply chain problem as it is a technological problem. And so the architecting of an exploration program has to be centered around logistics and supply chain and how we're going to keep crews healthy and alive and productive and accomplishing what we want them to accomplish in long-duration spaceflight. This is just a diagram to show why we think missions like ARM, for example, the asteroid redirect mission, are going to be important to us. Already ARM has showed us through the analysis of where we would fly it, where we would return the asteroid, of the importance of a lunar distant retrograde orbit as a staging area for future deep space operations. This big figure just shows you the relative gravity wells of the moon and the Earth and identifies locations, if I could say it that way, in that environment that are ideal for in-space transit, in-space transportation, the moving of large masses from one location to another. The distant retrograde orbit to which the ARM will return the asteroidal mass is going to be one of those areas that we can test out our capabilities to conduct and stage operations, and we will eventually use that and use that same SEP hardware, solar electric propulsion hardware, and maybe even the same bus that we use for ARM to be able to, in the future, repurpose it for missions into deep space from that distant retrograde orbit. And this is, again, just to make that point that ARM, after redirect mission, is a stepping stone to high-powered SEP needed to move large masses to and from the Earth system to the Martian system. This is a couple of slides to show you how we were thinking about that, and I'll just flash through this quickly because this is actually how we would do it. There's, I'm told, some orbital mechanics problems with this graph, but it makes the point that we want to make, which is that we need to study and exercise these different orbital mechanics and orbital pathways in order to efficiently move large masses to and from the Earth system to the Martian system. And it's become apparent to us that a split mission concept is probably the best way to go, where we would send large masses, cargo, even a future return ship to Martian orbit through the SEP bus, through the SEP technology, where we could take the long times for moving these masses that a SEP system would require, and then use the chemical systems, the short mission durations, to move the humans to and from staging areas in cislunar space out to the Martian system. And so the architecting all of this is something that requires a lot of thought, a lot of analysis, and that's the work that's ongoing under the rubric of the Evolve on Mars campaign you may have heard about that Jason Crusan is running, which is essentially a series of studies to answer questions about what is the optimal way to accomplish these transits and to identify the kind of masses we need to be, for example, be able to get not only from Earth to Mars, but from Martian orbit to the surface and back to Martian orbit again for the return trip. This then is our goal, to expand human presence into the solar system, into the surface of Mars. This is a conception of what it would be like if you were an astronaut standing on Phobos and how Mars would appear in your view. And one of the things that's part of the equation going into this Evolve Mars campaign is how would we use, for example, the moons of Mars as an interim step to the surface. So all these things are the subject of active study, but it's not just the studies that we're doing, but it's the actual hardware that we're developing with SLS and Orion and SEP and ARM that are the pieces that are going to take us to that ultimate destination. So the early pieces are being put in place. Again, the journey to Mars is a long one. This is a marathon and not a sprint. But if we're going to do a sustained program of space exploration, these are the kind of pieces we have to have and the kind of pieces we are, in fact, putting in place. And with that, I'll take the questions you might have.
We'll do that.
Or you're done? Sure. Okay.
Okay, the next person that you will be hearing from, of course, Jay Shin is not able to be with us here today, but we are left in wonderful hands with Robert Pearce. Bob is the Director for Strategy, Architecture, and Analysis in the Aeronautics Research Mission Directorate at NASA headquarters. From 2003 until July 2010, he was the Deputy Director of the FAA and led the Next Generation Air Transportation System, Joint Planning and Development Office. Prior to the JPDO, Mr. Pearce held various strategic and program management positions within NASA. And one interesting factoid about Bob is that just in a couple of days, he'll be opening up his house to host a person named Laura Del Rio, listen out for her, from Spain, and she's going to be playing professional soccer here in the United States for Washington Spirit. So welcome, join me in welcoming Bob Pearce.
Good morning. And I realized after I gave you that factoid that, in fact, the Washington Spirit hasn't announced that yet, so it's our secret that she's coming over to play for the Washington Spirit. So. Yeah, nothing in the papers. Nothing in the papers. Yeah. Okay. So, as Charlie mentioned, the 100th anniversary of NACA was just a little over a week ago. So, if anybody should be, in the undertaker mode, it's probably 100 years of aeronautics. But I got to tell you, we are, just as this conference said, we're on the cusp. There are new, important, and exciting opportunities for the future of aviation, the future of aeronautics, and I'm going to talk to you a little bit about that. So we are driven by strategy, and we've recently reestablished our strategy to look towards that next 100 years. And so we looked at what are the things that are driving aviation for the future, and it's these things that you see up here on the very left. It's issues in global mobility. In the last 20 years, the number of unique city pairs across the globe has doubled. In the last 10 years alone, the level of demand in the developing economies has tripled. If you look between 2011 and 2016, 800 million new passengers are coming into the aviation system. Half of that alone is from Asia Pacific, and half of that, again, is from China. One interesting sort of factoid, just to get a sense of the rate of development and how it's affecting things like aviation, but a lot of other industries. And I don't think I have this exactly right, but it's pretty close, that in the last 5 years, around the last 5 years, China has used as much concrete as the U.S. has in the last 100 years. I mean, it's an astounding rate of development. And a lot of that's for airports and for cities and so forth. Globally, urbanization is occurring at about the rate of 7 Chicagos a year. So that's the level of emigration there is from rural areas to urban areas. So it's a huge number of people, a huge amount of development that's driving demand, and it's also driving competitiveness. So if you look at the next 20 years, the amount of the economic potential of aviation in terms of sales of aircraft and parts is between $4 and $5 trillion for the next 20 years. If you add in all the service and spare parts and so forth, it's between $8 and $10 trillion. So no one is sitting on the sidelines. So we're seeing Russia, China, obviously Canada and Brazil are already in there. We're seeing everybody jump in. They want to be part of that our competitiveness is being challenged, and we need to find ways to remain competitive for the future. At the same time, because of that strong growth, we're seeing the environmental impacts, and so we got to address things like how is aviation a good neighbor relative to climate, relative to the local air quality, and so forth. And so we're going to be addressing those major issues that come with energy and environment as that system grows. And finally, on the far right is maybe the most exciting thing in terms from a technology perspective, that this idea of technology convergence, that there are many industries, in automation, computing, communications is one. The energy industry has major accelerations in certain areas. Materials and manufacturing, major accelerations. We want to tap into those accelerating technologies, bring them into the aeronautics space, and see what we can do to create all new futures for aviation. We'll talk a little bit about that. Okay, so from that, we developed our 6 thrusts for the future. The first one is to continue our support for the next generation air transportation system, the nation's approach to transforming the way in which we manage air traffic, and I'll talk a little bit about that. The next one is innovation in commercial supersonic aircraft. If you think about the expanding, these expanding city areas across the globe, the connections and so forth, we're taking longer and longer flights. We're taking, these city pairs are 14, 15 hours apart. There's a tremendous opportunity to increase the Mach number, to go faster between these city pairs, to add that to our logistics equation. But we got to solve some pretty big problems. Chief among those is the sonic boom. Right now there's a prohibition about flying supersonically over land because of the sonic boom. So we're working with the FAA and working with the ICAO to see if we can't demonstrate that in fact we can build airplanes, we can shape those airplanes to minimize the boom to just a sort of a low rumble from the sharp bang it is today, and actually be allowed to fly supersonically over land. We're pretty close to proving that out. There's a one very important step, which is to fly a demonstrator, and we're looking at how we might do that. So there's a tremendous opportunity. There's a lot of excitement that starting with a small aircraft with business jet, but moving on up as time goes on to large passenger-sized airplanes. At the same time, we are doing a lot of work in ultra-efficient commercial vehicles. Getting the energy efficiency up, and I'll talk about one example in that area, while we get the noise and the emissions out. At the bottom 3 are kind of the new, and those top 3 we've been working at for quite some time. The bottom 3 are some of the new areas that we're really going after. Transition to low carbon propulsion. Part of that's about is doing our part in validating and characterizing drop-in alternative fuels that can get carbon out of the energy chain for aviation, but also to pioneer low-carbon propulsion technologies. And I'll talk a little bit about other propulsion cycles that we can think about going into the future that could change the way aircraft are propulsed. Real-time system-wide safety assurance. Think about the Internet of Things, right? And everything is going to have embedded computing, embedded sensing. We're networking all that together. And there's a lot of economic benefit that's coming with that. Well, we're doing the same thing in aviation. But we can overlay very sophisticated algorithms to understand the safety state of the system and to manage in real time what's happening, what that state is, where the potential hazards are, where the potential risks are, and to mitigate those. So we've got an extraordinarily safe aviation system today, but we can even do better by using those kinds of techniques, and we'll be pioneering that. And then finally, assured autonomy for aviation transformation. Let's bring the idea of machine autonomy into an extraordinarily safety-critical system. It's a really hard problem, but one that if we can do it, has tremendous promise. Right now, a lot of that's focused on UAS, and I'll talk about what we're doing in unmanned aircraft systems and give you a sense of where that's going. So let me give you an example of what we're doing to reduce emissions. This is at the upper end. It's a busy chart, but I kind of wanted to give you a sense of how we went from concept to large-scale testing, proving it out with the industry so that they can apply this confidently in new products. So if you look at the upper left, that's a hybrid wing body aircraft. So when we set out the metrics and we say, hey, we want 50% reduction in energy and we want 70% reduction in NOx and so forth, it drives you to think about different configurations. And the reason you might want to think about something like a hybrid wing body is, believe it or not, if you look at the wetted area of that, it's actually less than a standard tube and wing airplane. So the volume you can get for the wetted area is much less, and if you get less wetted area, you get less drag. And so that's a great concept. Unfortunately, while it's very aerodynamically efficient, it's not very structurally efficient, right? So a circular cross-section obviously is a great efficient way to take pressurized loads. That doesn't have that kind of cross-section. So one of the big challenges is how do you create an efficient structure that can actually get there? So what we're doing is, you see on the second block over, developed the structural concept. It's built around stitched composite materials. Did the fundamental work to show that those stitched composite materials could work. You can see on the right-hand edge here, small scale testing, curved, a curved section, a pressurized box, and so forth, proving out at small scales, and at the same time building the models and proving the physics and building those into validated physics-based design tools. So we can do that along the way with these small scale. But then you can see towards the bottom, we actually built a near full scale box that, if you look at the hybrid wing body up the top there, it's kind of that middle section is what you're seeing. So it's a multi-bay box, very large scale. It was delivered just recently on the Super Guppy to Langley Research Center, and it's now installed in the Combined Loads Test facility there. So that far right box, if you look at that upper picture of what that concept looks like, that is exactly what's in the Colts facility. So it's very large scale. It just barely fit. It was designed that way, but it barely fits into that facility. It's going to be pressurized, and it's going to be loaded, and eventually it's going to be taken to failure, and we'll have that near full scale data to validate that in fact the structural concept works, and therefore that vehicle works. Hopefully, if we can manage it, we would like to actually go out and build and fly an X airplane of that configuration or a similar configuration. So that's the approach, and that's the kind of results we're seeing as we bring some of these things to high scale. So we've just recently installed a test article vertical tail on a 757 in cooperation with Boeing that's using active flow control. So we're actually blowing the surfaces, increasing the effectiveness, which will allow us to reduce the tail size and reduce the drag, and a number of other examples where we're taking these things to large scale and testing them out. So tremendous progress in the last couple of years on some of these technologies that will allow aviation to reduce its energy consumption and its emissions by large factors. At the same time, we're also working with the FAA, as I mentioned, on next gen. On the upper left-hand side, you can see something called the tailored arrival concept. So what you want to do is when you're arriving at an airport, you want to stay at a very efficient cruise altitude, and then you basically just want to pull the throttles back and glide in for a landing at the airport. And you can do that today. They're called optimum profile descents, but you can only do them if you're like the only airplane in the area, because it's really hard to coordinate all of these airplanes doing this at the same time. But that's where you get the benefits, is when you have all the airplanes coming into a very crowded metropolitan area, all performing that kind of an operation. So what we've done is, down the lower right-hand corner, is built the tools that allow the controllers to actually do what's called path stretching. So at your optimal cruise altitude, you want to just stretch the path a little bit so that each airplane gets aligned properly at the top of descent, and then can enter this very efficient arrival pattern. So we did that work. You can see the types of things tools we've already built, like the traffic management visor that we already developed and is out in operation with the FAA, and we added things like controller managed spacing. And then we just recently transferred that technology to the FAA, and it's in their acquisition management process. So we're doing things that are real. We're taking these it's not just about the research, and it's not just about the technology development. It's about making sure this stuff is getting out, it's getting into the system, it's making differences and making impacts, and that's what's happening. So tremendous success over the last several years, and we're taking that success and we're building on it. So a couple of things we're looking at going out to the future. This is low carbon propulsion. And basically, one of the concepts is hybrid electric propulsion. So basically, a Prius in the sky, right? One of the things you can do is so electric motors. One of the benefits, right, is they're scalable, right? You maintain the efficiency of that motor at just about any scale. So now we can essentially distribute propulsion across the airplane and get very, very high bypass ratio. So today, good engines got about a bypass ratio of 10, and bypass ratio is kind of the measure of the efficiency. It's how much flow is going through the fan stage, and that's how you get the efficiency out of the engine. you know, with this kind of a concept where you're using electric motors and you're distributing it, you can get an effective bypass ratio of about 100, so maybe about a 10x increase in bypass ratio and the efficiency that goes with it. There still is a very high efficiency small core turbofan to produce the electricity that drives the electric motors and so forth. So if we can do it, studies are showing that we can get these kinds of benefits at the bottom, a 60% reduction in energy usage, 90% reduction in emissions, and about a 65% reduction in noise. So huge benefits. Lots of different ways we can integrate this. This is an area of convergence, right? So we're looking at what's coming out of the energy industry, especially in the area of battery production. If we can get from about 200 watt-hours per kilogram, which is what you can get with the best lithium ions today, up to 800 or 900 watt-hours per kilogram, which is, you know, about a 10, 15-year kind of horizon is what they're looking at for some solid-state type batteries. We can actually enable this kind of a configuration. So tremendous opportunities, and that's one we're going after. Finally, I just want to talk a little bit about what we're doing, some of the things we're doing on autonomy. Obviously, everybody's aware of what's happening with UAS, especially small UAS. Probably a lot of you probably have one or two. And there's a lot of potential huge benefits, right? So up in the corner, I know you probably can't see it too much with notional scenario. You know, there's a lot of things from search and rescue to pipeline monitoring to, you know, aerial photography. Lots of things that can be done with these. But the problem, of course, is they want to be done in not just out in rural areas, but they want to be done in urban areas. And making sure that those vehicles are actually flying where they should be flying, that they're not creating safety hazards to the rest of the aviation system, but also to each other. They're not going places they shouldn't go. We need some system to coordinate all that. So one of the things NASA is doing is we are just starting down this path of actually building a UAS traffic management system. So it's very own traffic management system, low altitude, about 1,000 feet and below, the ability to coordinate all of these vehicles so that they operate the way they should. So quickly, actually, in the next year, we're going to have a first build of this, and we're going to continue to build this out so that in the near term, in about the next 5 years, let's safely enable this burgeoning market to actually happen. And then the long term, we want this to be autonomous, and so we can accommodate this at very massive scale. You can see kind of the builds. I won't go through it all, but the idea is to build a little, test a little. But one of the exciting things about this has attracted a lot of attention. We've got agreements with Google, Amazon, Verizon, 3-Door Robotics, Airware, FAA is working with us, NOAA is working with us. We got the Department of the Interior because they'd like to use it for a lot of their operations in their very remote parks. The insurance industry is coming in, obviously academia. Everybody sees the potential of this market. They see what we're doing as the critical component to actually making it work, and they're joining with us in this process. So this is something to watch. We're going to be doing this over the next several years, and I think it's going to be a very exciting development. So those are a couple of things. As we look to the future, very low emission, sustainable, transformative, let's go fast, let's go supersonic, but let's also take advantage of these transformative capabilities that UAS is bringing. Not just for small vehicles, but ultimately for passenger transport. Let's get to small, on-demand passenger transport. Let's get to single pilot operations for large aircraft and so forth. So there's a lot that can be done, a lot of transformative opportunities. And if the U.S. leads, we'll stay at the forefront of this market, and it's a huge market for us to stay at the forefront of. So we do all this in partnership. So just in summary, you know, we think we're on the right path. We've got a tremendous number of innovative solutions and technologies in the works, and we're delivering results. And so we're really happy to be here to talk about this and happy to talk about it some more, either during the question and answer period or offline. So thank you very much.
Thank you. And obviously someone likes what they're doing because they got a budget bump up this year, a significant budget increase. So that's a very good thing. So most of you out there know that Rob Strain was able to entice Mike Gazarek to come and join him over at Ball Aerospace. And so Robert Lightfoot and Charlie were able to draft Steve Jurczyk from being a center director over at Langley Research Center to move his family to come up to DC to head the Space Technology Mission Directorate. So we are very happy to have him in place. So Steve is going to be the AA of the Space Technology Mission Director. He is now officially in place, and I guess March 2nd was your first day. The director is responsible for innovating, developing, testing, and flying hardware for use on future NASA missions. As I said, he previously served as Center Director of Langley Research Center, and before that, he served as the Deputy Center Director under Lisa Rowe. So the one interesting factoid about Steve is that he is an avid snowboarder, believe it or not. In 1992, he was out in Colorado and took one lesson, and he was hooked. So now he enjoys doing that with his daughter. Please join me in welcoming Steve Jurczyk.
Got it. All right, thank you. Well, good morning. This is my 8th day on the job. And so I'm in the honeymoon phase, also known as the blame the previous guy for everything that goes wrong phase. Actually, nothing that I deserve no credit for anything that you're going to see here, except for a little bit of small stuff that Langley did, right? The credit really goes to Bobby Braun and Mike Jurczyk and many others, right? So the interesting thing is I'm really good friends with Bobby, because Bobby spent a lot of his career at Langley Research Center before he went to Georgia Tech, and we're good friends. I immediately, I think like 2 minutes after it was announced that I was the AA, I got a text from Bobby from California. He's actually on sabbatical at Caltech right now. And then I hired Mike Jurczyk into the agency. So I hired Mike into the engineering director at Langley when I was the director there, and Mike was working on an instrument that we were flying on an aircraft, an interferometer, when he worked for MIT and Lincoln Labs, and that's how I got to know Mike. So those guys both did a great job, because if you look at the history of cross-cutting technology programs in this agency, it's a rough history, right? So you talk about a program that goes from dare taker to caretaker to undertaker more rapidly than any other program in NASA, it's cross-cutting space technology. Okay, so we're in the 5th year of the program now, and it's a credit to Bobby and Mike and the centers and industry and academia and our government partners and even our international partners that the program has accomplished what you're going to see here and is poised to really enable exploration and scientific discovery as we move forward. So it's real credit. So I just wanted to give credit to those guys and to everybody who's contributing to the program. Let's see. I'm going to switch gears for a second. So we have multiple elements that in our program that are really, really important, some that we've inherited and some that we started from the beginning. So we're the central home for SBIR and STTR investments. And I think we've really done a better job over the years of leveraging those investments, not only to stimulate small business, but also back into our missions and back into getting our work done. And we need to do a better job of doing that. I was looking at some data, actually, when I was Center Director at Langley. So right now we have 19 Phase 1 and 2s in Maryland, 51 Phase 1 and 2s in Virginia. And which is impressive. Virginia's the state with the second most Phase 1 and 2 SBIR and STDR awards, and over 100 in California, and all over the country. So it has and will continue to be an amazing program. We're really looking at public-private partnerships to stimulate research and technology development, and I'll talk about a couple of things that we're looking at doing moving forward when I get to what we're going to do in the future. We are engaging the brightest minds from academia. Our Space Technology Research Grant Program, I can't tell you how competitive our Space Technology Research Grant Program is in graduate students applying to that. And the quality, and I can't I can't do justice to the quality of the students in that program. We're making basic investments in technology. The list that Greg showed of things that enable exploration, you'll see that list reflected in the thrust areas that I'm going to show and I'm going to talk about. That list is in there. And then some of the missions that John talked about, some of the future missions, I'm going to talk about some of the things we're doing in observatory technology to enable those future missions. And we are absolutely also here to enable commercial space, to take what we do for NASA and leverage it in commercial space and work directly in partnership with the private sector on stimulating a robust commercial space sector in this country. They say a picture is worth 1,000 words. A video is worth, I don't know, millions and millions, John? I don't know, something like that. So the first thing I'm going to do to show you some of the things that we have accomplished and are going to accomplish in the near future is show a short video. So I think if I click, it's going to play. 5, yes. 4, 3, 2, 1. And liftoff at dawn. Very well done video. So again, I take no credit for the video, but it was very well done and I had to use it. And you can just see the breadth of technologies that we're working on with the budget that we have and the value that we're delivering, not only to the agency, but to the nation. So this is, I love the Earth-dependent, proving ground, Earth-independent theme and chart. This is a version, sort of a version of that for space tech. And it's go there, land there, and live there, right? And we got to get there We got to land much larger mass systems on the surface, and we have to. We're going there to live. We're going there to at least in the near term. We're going to stay there for some period of time. So you saw in the video some of the go there technologies, and one large one for us is solar electric propulsion. It was high power solar electric propulsion. It was already mentioned, and we've developed. You saw in the video the two large solar array concepts. Deployable solar array concepts, as well as some of the electric propulsion engine technology. Right now, our plan is to do that flight demonstration as part of the ARM mission, and we're really excited about that. We're also going to issue a solicitation in the near term, which I'll talk about on the next chart, which could be really exciting for advanced propulsion. Talked about the asteroid redirect mission. That is a great opportunity to demonstrate SEP. One thing, so I spent my summer vacation about 5 or 6 years ago on the Human Exploration Framework Team, Phase 1 in Houston, Texas. Not the greatest place to be in the summer, but I remember this meeting we had, and actually that was led by Dan Dunbacher and Steve Altimus, Brent Sherwood from JPLC, he was on the team, James Roy was on that team, he's my deputy now, and I remember this presentation we got from the systems guys, I think it was Brent Houston, and Brent showed us the big gear ratio that you can get with solar electric propulsion because of its efficiency. So low thrust, you're not going to get anywhere fast, but for moving things and positioning things, it's great. And it was like a duh moment for us. It's like, this is a technology that we need to pursue, and we have. So a little light bulb came on down in Houston, Texas. Working on a lot of entry, descent, and landing technologies. So next year, we're going to celebrate the 40th anniversary of Viking. Viking was actually led out of Langley. Langley developed the 2 orbiters and 2 landers, Jim Martin, Tom Young, and Gus Gustafaro. And 2 of those gentlemen are still around and still active. I talked to Tom. Actually, Tom is from and lives on the Eastern Shore. When I go over there, I have dinner with Tom and his wife often. He's an excellent individual. And Gus is still active at Langley. So we're going to celebrate the 40th anniversary. And those guys were what they did was amazing. If you look at the engineering tools they had and the fact that they were successful, and we're the only nation to be successful landing on Mars, right? It's amazing. We are still using the supersonic disc gap band parachute. We're still using the same entry vehicle, the same plan form for the entry vehicle, the 70-degree sphere cone. JPL and the agency has done a really nice job innovating the terminal descent and landing part of EDL, right? The airbags and now the sky crane. When I show people the video of the sky crane and they say, that's never going to work. And I says, it has worked. Okay, we've landed a 950-kilogram nuclear-powered rover the size of a Mini Cooper on the surface of Mars, and it's roving around now making incredible discoveries. So the Viking guys did a great job, but we've come to the end of the line of what we can do with the Viking technology, right? Even innovating in terminal descent and landing. Because we're going to need to land 15, 20, up to 40 metric tons on the surface to enable human exploration of Mars. And I think John would like to land 2 5 metric tons for science missions, including Mars sample return. So a lot of technology there. We demonstrated in 2 sounding rocket flights at a while in a hypersonic inflatable entry vehicle, actually Langley did that one, and then we had a flight out of Hawaii of the LDSD. Charlie mentioned this, and we've actually tested 2 parachutes on rocket sled out at China Lake, and successful tests. Going to down select one of those supersonic parachutes and fly again in June. JPL is going to do that. So we have a robust EDL, and I'll tell you about where we're headed in the future with EDL. Optical comm, led out of Goddard, LCRD. It's incredibly exciting technology. It can really, I think, revolutionize the telecommunications industry with very high bandwidth communications capability, reliable, very high bandwidth communications capability. So when we get to fly that, it's going to be incredible. We're doing a lot in environmental control and life support systems, particularly on station. We need to get near to closed loop life support systems for the trip to Mars. I'm going to talk about, I'll talk about MOXIE. So MOXIE is a ISRU demonstration on Mars 2020 that was solicited through the science payload solicitation and selected through that. And it's going to generate oxygen by extracting it from atmospheric CO2. And we just had an instrument accommodations review actually at JPL for the MOXIE instrument on the 2020 rover. Let's see. Robotics and autonomy. You know about Robonaut on station. We had a discussion yesterday, actually, with the station JSC guys about how we can actually make Robonaut reduce astronaut workload for mundane tasks so we can have the astronauts do more science and more tech development. And so that's really exciting. So we're going to move that technology from development into practice and operations. So we're excited about that and other technologies that we're going to need. So I'm going to move on to the next chart. But we do have, coming up, we have a lot of exciting missions. In addition to LDSD and development of SET, we have GPIM, the Green Propellant Mission, demonstration mission led by Ball Aerospace. We just completed the 5.5 meter cryo tank development. So we tried to develop a composite cryo tank in the 90s and kind of didn't get there because of the technology and also the configuration we were trying to manufacture. We successfully developed a 5.5 meter cryo tank, structurally tested it at Marshall, cycled it cryogenically, and succeeded. And so that's a real enabling, enhancing technology, particularly for launch vehicles. And part of that was part of the advancement there was technology that was developed by Aeronautics Research Mission Directorate and composites. Bob mentioned the Pearce work, the composites for non-circular fuselages. So one of the techs that enabled that was out of autoclave processing, right, which significantly reduces the time as well as the cost of processing composites. We're also looking at robotic layup of the carbon fibers. So basically you send the CAD file and you can lay up the fibers in one direction and then another direction, another, and optimize the structure based on where the stresses are going to be. And we're pursuing that technology with ARMD. So there's a lot of other projects coming up and exciting things coming up and exciting things we've already delivered on. Okay, so here's, so Bob had his 6 thrust areas in Aero. This is the closest things that I have to thrust areas in space tech. And so we already talked about high-powered solar electric propulsion. We're going to issue a solicitation, hopefully very soon, on advanced concepts, system studies for advanced concepts for reduce the trip time to Mars by 20% as compared to chemical propulsion, at least 20% over chemical propulsion. So we're really looking for advanced propulsion concepts and technologies, again, to get the trip time down, and so that solicitation will be coming out here soon. We do need to do that. I talk about space optical comm and how enabling it could be. Advanced life support and resource utilization. We did a blue sky event. It was kind of an underground blue sky event about 2 months ago, or 3. Actually, it was before the first of the year, back in the November-December timeframe, and we called it ISRU to the wall or ISRU on steroids. So we looked at what could we produce, everything from oxygen to LOX and methane and hydrogen to growing crops on the surface to using 3D printing to manufacture things from regolith, right? Everything you could possibly think of, and then said, well, what architectures does that enable, and what systems are in those architectures, and what technologies enable those systems, and some very interesting results. So we presented that to Gerst and Greg, and it's going to go into the human architecture team, into their hopper, and we're going to, so I think what's going to come out of that is some really great challenges for space tech with respect to ISRU. Entry, descent, and landing. This year, starting this year, later this year, so we have a pretty broad portfolio of technologies in EDL. We need to it's time, and we've demonstrated a lot of those, HIADs and SIADs and supersonic ring-sail parachutes, et cetera. So I think it's time to maybe focus down, and so Langley, JPL, and JSC are going to lead an EDL system studies to look at the architectures and that are enabled by the technologies that we developed or will be developing to land 15, 20, or even up to 40 metric tons to the surface. And that system study will inform us on what to focus on with respect to a candidate architecture or architectures, which we might demonstrate on the Mars 2024-26 mission or some other demonstration, and also what technologies I need to invest in and to take further along to enable the large mass EDL systems. Talk about space robotic systems. I also, like Bob, we can leverage what Bob is doing in autonomous systems, as well as what's going on in academia and industry on highly autonomous systems. There's expert systems, AI. We've talked to the IBM guys about how to leverage the Watson technology, et cetera. So we think that, again, like Bob said, for Aero, for space, it's space robotics and highly autonomous systems are an enabler. Lightweight space structures, I talked about the 5.5 millimeter cryo tank. One thing we're in formulation on is the composite enhanced upper stage for SLS, which would be kind of a evolution of the SLS upper stage that we're hoping to get started here in the next year or two. And again, we're taking advantage of those innovations in like out-of-autoclave processing composites, robotic layup of the fibers to improve the performance, reduce weight, and also reduce the cost of producing some of the primary structure for the CUS. Deep space navigation, John mentioned that. Another project that JPL is working on is Deep Space Atomic Clock. They're in INT right now, in environmental test, troubleshooting some noise problems, just like you would always have in INT. I don't think there's anything unusual there. And we're looking forward to flying the Deep Space Atomic Clock in the not too distant future. And then with science, we had an early stage workshop actually out in Crystal City. I guess it was last week, and we had some of the folks who are working on technologies for astrophysics and heliophysics come in and present their progress. And I could not be more impressed. I was only there for a half a day. Christyl, you were there, yeah. I could not be more impressed with the 4 or 5 presentations that I saw. I mean, there's a small company in Maryland is developing this detector technology where they have the noise floor down where they can do photon counting. That is just really cool and really great technology. So I'm really excited about not only enhancing and enabling the missions for astrophysics and helio, but also planetary. And we're going to start very soon here working with Dr. Mike Freilich and George Komar in the Earth Science Technology Office on how we partner and can enable Earth science with cross-cutting technology development. So that's what I have. I'm really excited to be in the new job, day 8. I loved Langley. I got to tell you, I was only center director for 14 months. Felt like 14 years. Yeah, 14 months. I was in the office. I've been in the office of director for over 10 and a half years, and most of my career, most of my 27 years in the agency has been at Langley, except for 4 years. Three was at Goddard on the Landsat 7 project, and 1 at headquarters in '93, which was a little bit too early in my career to be at headquarters. But now it's okay. You know, I'm just really excited to be here, and you know, we celebrated the NACA 100th NACA. I'm sorry, the NACA guys, the NAC guys want us to say NACA. So NACA 100th anniversary, 1915. The NAC was established because the Europeans were getting ahead of us in aviation technology, aircraft technology. In 2 years, Langley will celebrate its 100th anniversary. So the Langley Memorial Aeronautical Laboratory was established in 1917 as the first field lab for the NACA. So I'll have to go back for that. The one thing I'm really miss about Langley is the people. I love the people there. Of course, all the centers have great people. Headquarters has great people. All your organizations have great, but I've been with those people a long time. My leadership team for 10 plus years. I'm going to miss them. But you know, in the charter for NACA, there's this statement: to supervise and direct the scientific study of the problems of flight with a view to their practical solution. I just love that statement. It just kind of nails it, right? It nails what they were asked to do, and it nails what they did. And so that's what we're here to do in Space Tech. We're here to solve the problems of exploring the solar system, and with innovations and technologies to enable robotic, you know, future robotic and human exploration of the solar system and beyond. So thank you for your time.
Okay, it looks like we may have just a couple of minutes for some questions, if you have some questions of the panel members here. Does anyone have a question? Any of the students lined up back there? Yeah, and John actually mentioned you all. He was sorry that you all weren't able to participate in his presentation. Yeah. That's great. Question over here.
A few years ago, NIAC had a phase 1 that was successful, and I think it went on to phase 2, which was using, I think it addressed the low density of Mars atmosphere. It was looking at flapping wing technology, you know, and use for sensors and other atmospheric low-density atmospheres. Is Aeronautics or George Kumar's office or anybody like that leading any continued look into that to do cross-cutting or that nature?
So, do you have an answer? I want to start with SMD. I want to start with John. Do you have an answer, or do you want me to just? Go ahead. Okay. Okay. So my answer is I don't know. However, we're constantly looking at ways to explore Mars in more effective ways. So actually, Bobby Braun led I guess it was a Mars Scout proposal years ago for a Mars airplane, right, to be able to do regional studies of Mars. It was in collaboration with JPL. Greg Vane is right there. In collaboration with JPL, and so there's been concepts to be able kind of bridge the gap between orbiters, where you get global coverage, but at a spatial resolution that's fairly coarse and an accuracy that's fairly coarse, although the instruments just get better and better, so I got to be careful. And rovers, which you can rove over miles and tens of miles, right? To do regional studies, like the Earth Science guys do with their airborne research campaign. So we're looking at we've looked at rocket-powered airplanes and propeller-driven airplanes and flapping airplanes. We've looked at helicopters, and so I think we'll continue to look for opportunities to kind of more effectively explore Mars and bridge the gap between orbiters and rovers.
And we'll certainly work in partnership, bringing the expertise of the aeronautics domain to the table. So when we're looking at those kind of concepts,
I think if you look at, I don't remember what the name of the show is. JPL, is it Extreme Engineering or? Anyway, there's a little clip of a prototype UAV. It's a coaxial helicopter flying in a Mars atmosphere in a chamber at JPL. So that research is still going on, and it combines aspects of aero, of space tech, of robotic autonomy, and Mars exploration. And that's the kind of thing that we're pushing pretty hard, are these cross-cutting efforts. So maybe a helicopter on Mars.
15 years ago when I came to Goddard, formation flying and constellations were the hot topic. And since then, the spacecraft technology has gotten much smaller. 6U CubeSats are all the rage now. And I'm just curious about our concepts for doing distributed satellite systems, clusters, formations, constellations. Are those coming back because the technology is almost there now?
Oh, it's not just almost there. We're flying them.
Mm-hmm.
So in the interest of time, MMS is 4 spacecraft. They're very large, flying in formation, but we're soon to launch the Cygnus spacecraft. That's 8 missions that'll be flying in a formation and synthesizing the data of what would be a much larger capability. And of course, on the International Space Station, we're constantly upgrading and doing experiments with the Spheres experiment. And a number of people are doing CubeSat proposals, and a few people flying constellations of CubeSats.
That's right. Okay, we have a last question by Matt Mountain over here.
So all 4 of you represent senior leadership across the whole of NASA, so the whole of NASA is represented by what you there. So given that the title here is On the Cusp, What's Next, what do you foresee as the greatest single challenge NASA faces in the next decade?
Good question. Go for it.
That's a destination. I think the greatest challenge, I'll go out on a limb. I think the greatest challenge that we face is the education of the American people and education around the world. We are constantly fighting a battle of people being knowledgeable enough about basic science and engineering and math to be able to function in a modern society. And I think when we win that battle, and it's a constant battle, then the challenges of getting human explorers to Mars or discovering whether there's life on a nearby exoplanet, those are technical challenges that we know how to solve. The human problems are much harder.
Yeah, I would agree with John. So I go give, as Langley Director, I would give general public talks. And I invariably have somebody stand up and tell me, why do I want to go to Mars? Why are you spending my tax dollars on going to Mars? So I always start with spin-offs, the more down-to-earth practical things that we do in the Earth science, but always end up with Well, in the history of the world, you know, great nations explore. That's what they do. And when great nations stop exploring, it's the beginning or the beginning of their decline, right? And so, you know, we've led the world up until now, and I think we need to continue to do that. And great nations explore, and we need to continue exploring and pushing out. And we need to tell stories like we talked about earlier, and articulate it in a way to bring in the broader American public. You know, we're preaching to the choir here, but bring in the broader American public into that, in support of that.
Bringing in the broader American public also helps with our legislators. We have to educate and educate and educate them as well. So I'd like for all of us to thank this panel member, all these panel members.